You're going to learn about drilling. Isn't that what you lie awake wondering about? How do they drill wells? How do you drill oil and gas wells? So our focus is going to be talking about drilling and completing wells. And we're going to talk about oil and gas, but what you need to expand your mind and think about is that we use the same technology for drilling water wells, for drilling geothermal wells, for drilling wells where we're going to inject carbon-rich materials permanently and inject them in the ground. So it could be CO2 or it could be biomass waste. So there's a lot of aspects of drilling technology. We could be drilling down to explore for lithium brine, and we would use a lot of the same technology. So we're using oil and gas as the lens for this, but just think the extraction process and some of the exploration tools I talked about on Monday get used for other things too. So we're going to talk about how practices have changed over time, how to onshore and offshore differ from each other. We're going to talk about hydraulic fracturing and horizontal drilling, what's good and what's bad. There are good and bad aspects, definitely. And again, so the idea of horizontal drilling and hydraulic fracturing is opening up, remember, enhanced or unconventional geothermal. We couldn't be doing that and be delivering baseload green electricity if we hadn't figured out, I'm not defending oil and gas, but I'm just saying that all the technology pioneering happened in oil and gas, and we're moving it over to geothermal now. Environmental impacts of drilling and completion, how are they regulated in the US? And some other countries do it as well as we do, and some of them do it less well than we do. Surprisingly to some of you, maybe our standards of regulation are actually very good. So one of the interesting things about policy is, first of all, we have to create the policy, and then we have to have the staff to enforce and support the policy and to oversee it and to have really intelligent, well-intended, high-functioning people working in permitting offices to make sure that regulations and policy are properly implemented. And so I think when you get the opportunity, for some of you already have, and I hope many of you will go out and work in industry, the importance of good regulation is a really important part of any business, whether you're a medical practitioner or whether you're involved in energy development of any kind. Policy is really important, but having the funding and the standards and the cultural benefits of having really respected people in regulatory enforcement is part of what's required to make it all hold together. And we're moving through where we left off on Monday was talking about exploration and how the land side works. And here we're talking about site drilling and completion. And so we're going to cover these topics. And there's a lot of lingo in this class, and even just on the subject of oil and gas. So we're going to make a distinction between logos of companies and up in the upper left that are big oil and gas players. There's some that specialize, that are just drilling contractors. So if Exxon wanted to drill up a big area, they would contract with H&P or Neighbors to be their drilling contractors. It's not uncommon for the big companies like Shell or Exxon to have some rigs they control themselves and to contract for some of their activity with third-party drilling specialist companies. There are companies that specialize in the completion of wells, and some of those, so SLB used to be called Schlumberger, and then Halliburton, those are companies that complete wells, and they also specialize in collecting a lot of that wellbore data that I showed you in our lecture on Monday. And then producers, owner-operators of wells include companies like ExxonMobil, BP, and the list of companies you see ranked here on the left. So these are the global producers based on revenue of oil and gas combined, and just showing you based on their revenue who are the biggest companies. Now remember, as a country, the US is the largest producer and consumer of oil and gas, but this is at the company level and letting you know who the biggest players are. In the upper right is showing you the trends as we've gone horizontal of what percentage of all wells are drilled non-vertically. So up until about 20 years ago, everything was vertical, and with our capacity to steer drill bits, which involves computing technology, remember I made the analogy, it really has paralleled the ability to steer drill bits in the human body, our ability to do that in the earth. And so you just see how that ratio has changed. So a theme I'm going to reiterate in these lectures, and even when I give the wind lecture, is what we call a well today is very different than what a well was 30 years ago. what we call a wind turbine today is very different in terms of its productivity and its sophistication than what a wind turbine was 30 years ago. And I have a slide you'll see in a bit where Tony and I were in business school together, and a guy named Pitch Johnson, who was a very famous venture capitalist, came into class one day with a Motorola cell phone that cost $15,000, and it made a call. It could not text, didn't have any apps. So again, we call that a cell phone, and we call what you have today a cell phone. So if you think of that as an analogy of how cell phones have changed, my argument is wells have changed, and wind turbines have changed, and solar panels have changed. We call them the same thing, but what they are and how productive they are and how intelligent they are has changed a lot over the last 30 or 40 years. On the lower right is making the point that this is showing how many feet do we drill. So vertical wells have dropped a little bit in terms of the average depth to vertical wells is what that's showing. And horizontal and directional wells, so it's really common for a horizontal well to have, if you measured the full length of the pipe, look at that, 16,000, 18,000 feet. You know, that's over 3 miles of pipe in the ground for a single well. And you think of managing that and everything about that, you know, those stages of hydraulic fracturing and all those everything you just saw in that video, doing that over a 3-mile zone underground, where your vertical length is usually around 1 mile to 1.5 miles down, and then the rest is horizontal, is pretty complex engineering. So this is also meant to contextualize when you think about, this is about the rigs. How many rigs do we have in the world? So globally, we've got 1,700 rigs. It shows you how many are in the US and the percentage that the US is of global. So kind of the narrative is, you know, most activity is onshore versus offshore, and it's much more oil than it is gas when you look at all those numbers, all right? So we got all kinds of details here about trends that we've moved from, we're going horizontal versus vertical, the depths or lengths are getting longer, and in terms of the drilling rigs, they historically have run on diesel-based rigs, and we are moving and shifting slowly but surely to kind of hybrid, diesel-electric and/or electric drive, which makes them much quieter, which is really nice. I've worked on drilling rigs for 3 winters. When I was much younger, straight out of graduate school, and they are, you know, you had to have a lot of ear protection to be very close to them because of the diesel generators on site. This is highlighting where are rigs active today worldwide. So it shows, it shouldn't be a surprise to you, given that I said we're the largest producer of oil in the world, that we would have a lot of rigs running in North America, largely in the US, but otherwise in Western Canada. Shows you rig activity on and offshore there in the Middle East. On the right-hand side shows you who has the most wells by a long margin, the United States. We've had a lot of incentives, remember all those subsidies? And a big thing, so we've had subsidies to have domestic oil production, and we have private ownership of the mineral rights. No other country has that, so it makes it much easier for us to evoke the transactions to explore and look for, you know, we have much more of a marketplace for exploration for oil and gas than other countries. So here you are, we're the #1 producer by a long margin, and for oil and for gas. So again, remember when I took this class 45 years ago, long before you were born, that was not true at all. We were importing 2/3 of our oil, and we weren't even using very much gas 40 years ago. So things can change. It takes decades to do it sometimes. Sometimes it can happen much more quickly. But that's kind of giving you a lay of the land of where we are. And then this is showing you the offshore-onshore mix. Onshore oil and gas production is about 30% of the whole. It's less in the US, and in the US, you can see we have very little offshore gas production. It's mainly an oil story in terms of offshore. As a geologist, which I will remind you is what I am, you know, when you think of the offshore environment, geologically, I think experience has shown is some of the largest reservoirs that have been found have been in the offshore environment in terms of what the paleogeology was and what we can see out there. But the conditions for developing some of the offshore oil and gas is in very shallow water on continental shelves, but some of it is in pretty deep water. At the end of this lecture, assuming I move quickly enough, I'll show you. And there was a video about the Perdido where we're not only drilling, in some cases we are operating in an environment where we've got 2 miles of water, and then we're drilling 1 mile into the earth underneath those 2 miles of water. So, I mean, it's to the technical challenges associated with that, to me, are quite extreme, and some of the risks and how you manage those situations are very different. I'm not much of an ocean person myself. Some of you are probably badass sailors and things like that, but there's a sense of when you're onshore, when you're on the ground, you can control things a lot better than you can when you're in an offshore marine environment. So we're going to get into drilling a little bit more. This is a former student and TA of ours, Kemp Gregory, who the point of this picture is to reiterate that drilling is not a casual activity. It happens 365, 24/7, snow, rain, sleet, sunshine. Okay? I worked on the Blackfeet and Crow Indian reservations in the winter. We had 30 below temperatures. I wore something that looked much more like a spacesuit than what Kemp has on. And I lived in a trailer on site. And 90% of my workforce was Native American. It was a very interesting experience. But thermally, it was a very interesting, I literally looked like, a big bubble person or something like that. But I think just to click on, and similarly, when I give the wind lecture, I will emphasize the fact that when you are installing a wind turbine, it is a 24/7, 365 experience. The only time you halt your cranes that are bringing the wind turbine components in, so they set up big lights so you can work at night to do it, is the hardest part about installing a wind turbine is that it's windy, right? And so you have to time it for when the winds have ebbed to be able to install the components of the wind farm. So this is a relatively new graphic we got from our Energy Information Agency, the EIA, which you will see a lot. And the EIA is not what it used to be. There's been a lot of terminations of some of the data talent pools there, but they're still producing some new graphics. And this graphic I thought was a little bit interesting because it helps you visualize, we go from having rigs that are drilling, and they track how many we have, to how many wells, and they look at how many new wells have we drilled, how much cumulatively have we drilled but not completed. So if you drill a well, but you don't complete it, we have a hokey acronym for that. We call it a DUC. And a DUC, if you drill a bunch of wells to get the economy of having the drilling rig there, just go bzz, 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 and drill them all at once, as you saw in the movie, you might want to wait to complete the wells and bring them online till the price of oil or gas is higher. Because when you do hydraulic fracturing and horizontal drilling, you are releasing, almost like opening a soda can that's been under pressure, you release a lot of oil and gas in the beginning, and then it goes on decline. So it's not uncommon to produce a quarter of the reserves you're going to recover from a well that's been hydraulically fractured, and when you bring it online, you get a lot of production at first, and then it goes on a hyperbolic decline. So you want to bring the well online at a time where the market is favorable to you. It's kind of a form of inventory management to drill in an economic way, but to complete the wells when you really want to bring the production online. So then we have completed wells, and then we have new production coming from newly completed wells, and then we have production from the existing wells, which it is always going on decline. You're always reducing pressure in the reservoir. So from the EIA's point of view, they're kind of trying to track information of what's going on at each stage in this process across our country, and it was just a new visual they created that I thought would be helpful. This is just making sure everybody knows when we say vertical, we mean vertical. And, we didn't drill the first truly horizontal well, until 1991. A company that today is Devon Energy drilled that well. They acquired Mitchell Energy, which really pioneered horizontal drilling. In order to drill, 80 years ago or 100 years ago, even in the Los Angeles basin, they did a lot of directional drilling that looks like the middle. And our offshore platforms, I went to UCSB as an undergrad, and the offshore platforms there, when you have offshore platforms, we weren't drilling horizontally at that time, and in general, they still, in order to maximize production from one platform, they would drill off directionally. So it's kind of the mid place between going horizontal. So I think I wanted to put this timeline on here to help everybody understand the time frame of going from your first horizontal to getting half of everything, horizontal or directional. That's how long it took. And then that's 2017. But today, 90% of all wells being drilled have a horizontal component to them. And so that's just an evolution of technology, of efficiency. One of the things that I'm putting this in early than I might otherwise in the lecture, but a really common question that gets asked about drilling oil and gas is, Well, what happens as you pull the oil and gas out of the rock? And some of the rocks that I passed around yesterday, and I think we may have some more to pass around, if you think of most reservoir rock having the same, most of it on average is like 13% porosity, that's the same porosity as concrete. So if you're drilling through concrete with a wellbore and you're pulling water or oil or gas out of that 13%, the concrete still has structural integrity just because so think of the reservoir like that. So people sometimes have the image that oil and gas occurs in underground swimming pools. And if it did, and if you fully depleted that, yes, you would have collapse, right, of the rock. But because your reservoir has a lot of rock integrity to it, it's like concrete, you don't get much. There are a few places where there is some subsidence associated with oil and gas production being removed from reservoirs, but it's very, very rare, actually. That's just highlighting what the vertical and the horizontal legs tend to be, and we should actually update that horizontal leg can be over 20,000 feet. So it's really gotten quite long. All right, so a bunch of the things I'm going to show you, I'm just going to say, I'm showing you this, but you do not need to memorize this. This is a lot of detail, and that is true of this slide. So this is showing most drilling rigs are what you see on the left. On the right is a new technology called a top drive. I'm just socializing that is out there. We're not really going to get into it because we have a lot of other stuff to talk about. It is more efficient. It is better in many ways. But 90% of the rigs in the US are still operating this way. We're going to talk about the drilling bit in a moment. And so it is heavy. This is a water well bit. And so we use drill bits for drilling in the earth, for water, for geothermal, for everything. And we're going to talk about, and material scientists are really important to drill bits because of the materials that are on the cones of the bit itself. Different rocks need different kind of bits, and the harder the rock is, the more high-tech the bit needs to be to cut through it. So you see the drill bit here. You see all the different key elements of the drilling rig, and one of the things that I want to point out to you, we don't have a field trip this quarter to an oil field. Sometimes we do. And the shallower the reservoir, the smaller the rig. The deeper the reservoir, the bigger the rig you need to have because the rig has to be able to support 30-foot lengths of steel pipe that are your drill pipe. So the rig has to be big enough to handle the weight of all that drill pipe. So the scale of the drilling rig is proportional to the depth of the well. So if you see a little itty bitty drill rig out there, they say, oh, they're probably drilling a water well, or it's really shallow oil and gas production. So that's just a broad idea, but there's a lot of complexity. This is technology that's been around since the 1860s. In the beginning, we used to just punch holes in the ground, and then the rotary rig was invented, and it's been refined and refined, and the top drive is the latest version of that. So this is a little bit more. Howard Hughes, who some of you have heard of. Baker Hughes is one of the oil and gas service companies in the drilling and completion space, is a remainder company of Howard Hughes, who was kind of an Elon Musk of his time, quite the ladies' man, very involved in the film industry, but made a lot of his money in early oil and gas technology and oil and gas development. So this is just showing different kinds of drill bits, talks a bit about, that the materials have very often diamond or synthetic diamond material because you want your bit, when you put it in the ground, to last as long as possible. It gets very hot down there with these drill bits grinding through rock. And if your drill bit is not working any longer, you have to pull many, many strands of 30 feet of drill pipe up, take the bit off, and then drop a new bit back down. And that loses you a lot of time and cost doing that. So having very effective drill bits is a very important part of oil and gas drilling, geothermal drilling, lithium brine drilling, things like that. This industry around drill bits, when I was in this business, ARCO would buy the drill bits and burn them out, and whatever they didn't use, they would sell back to Baker Hughes or wherever they got them from. Today, the industry has evolved, as many industries have, to a service model, which is there's a contract signed that says, we're going to work with you, Baker Hughes, to help us with our drilling contract or drill wells, and we will pay you for the footage of drill bit time that is used and how much wear and tear is on the bit. So the company, Exxon, doesn't own bits anymore. They just pay for the services that bits deliver. it's interesting to see how that's evolved. So this is it's another example where like, Jane, do I really need to know this? And the answer is, it's good to understand it, to say, how do we drill for anything? We could be drilling a well for carbon removal. We could be drilling a well for geothermal. But how does the mechanics of all this work? So just making sure that you see, that's the mud system. So we have something called drilling mud, which is like 98% water, and otherwise it's clay. And the drilling mud, there are people whose profession is to be a mud engineer, and it's to modify the properties of the mud largely to help make sure we're doing some of the things shown here, that the mud is cleaning and cooling the bit, and that it's helping keep all three, 2, 3, and 4 basically are the same thing, which is the weight of the mud in the borehole is helping keeping the borehole from collapsing. The properties, there's other properties in the mud that seal off the well bore and prevent anything from flowing into the well bore as well. So there's a weight aspect to the mud, and there's a sealing aspect to the mud until we case the well. A very important part of the circulation system of this mud is it brings cuttings up from, when you look at the drill bit, a key part of it is in the center of the drill bit. Drilling mud is flowing through and blasting through and hitting those cones and cooling them, right? And pushing the cuttings up the outside of where the drill pipe is. So you have a hole like this, right? You have drill pipe like this, and you have the bit on the bottom. The drilling mud is coming through the center of the drill pipe. It goes through those cones and cools them down, and the cuttings in the drilling mud come up the outside of the drill pipe. Does that make sense? So here's the hole. Here's the pipe. The mud comes down the center of the pipe. It cools the bit. Then it circulates back up out, and it carries the cuttings to the surface. On the surface are big things called shale shakers, which capture all the cuttings, and then the mud sifts out of that, and it just keeps getting recirculated and recirculated. But there are engineers, there's these trailers that are right outside what's going on, and I've sat on these and worked on these, where there are people who are the mud engineer, and their job is to make sure that the weight of the water column of that drilling mud is enough to keep the hole from collapsing, and to keep the seal of the wall of and because you can encounter pressures you don't expect, and if you know it's coming, you mud up the well, you make the mud more heavy and more dense. And as a geologist, we're there looking at all these cuttings under the microscope to see, under the microscope, you can see if the cuttings have oil stains on them or not. And so you can see what you're drilling through, and you can also see fossils and things that help you calibrate and say, oh yeah, we were expecting this formation at 8,000 feet. Yes, we nailed it. Or, oh shit, it's not there. And so the cuttings are a really important calibration tool as you're drilling a well, to try and make sure you know where you are as you're drilling. So this whole system, most people wouldn't know about it for obvious reasons, but it's just to help you understand the basics of it. And if you visited a modern well site, you'd say, wow, this is all really highly optimized to do this really well. If you saw it 20 years ago or 50 years ago, you might be a little bit, but it's a lot better. So these are really important. They are called blowout preventers. Because as I mentioned, when you're drilling, you can sometimes encounter pressures you did not anticipate. And so this is a stack of different shear rams, blind rams. There's another ram on here somewhere. But basically there's right here, it shows we have annular preventers, pipe rams, and blind rams. Usually have 2 or 3. These are highly regulated. The size of this stack of blowout preventers is proportional to how deep you're drilling and what you expect to find. It's all part of the permit process. You cannot start drilling a well until you have this all in place on your wellhead. And it's to prevent blowouts, which are uncontrolled flow of fluid, oil, gas, and water up to the surface. So there's a huge motivation to control that, and we'll talk in a moment that some of the worst accidents in the history of the industry, including something called the BP Horizon, was a failure of a blowout preventer, and that's part of the reason we have 3. So it's like this triple backup system to manage that. And much like airplanes don't crash very often, blowout preventers don't fail very often. So in general, this system of managing pressure surprises works very well in industry. Okay, another thing that works very well for modern wells, the issue again is older wells, is I added up 1 mile is 17 Statues of Liberty stacked on top of each other. And that is about how far we typically have multiple. So on the surface, we'll have a hole about this big that we start with. And then it telescopes down by the time you're several miles down in the ground that your wellbore is only about this big. And that's because we have the telescoping casing is there's a great amount of permitting that goes into to ensure that there's a lot of protection of aquifers. In the first aquifers where we draw water for human purposes tend to be in the first 2,000 feet, sometimes 3,000 feet from the surface. But in order to drill a well, you have to have a whole casing plan that demonstrates and proves that you are protecting any water supply from any contamination from drilling mud or any oil and gas that might leak out from the wellbore. So very low issues around this with modern wells. The issues we do have around this are with older wells and where the cement that supports the steel casing in place, sometimes the quality of the chemistry of that cement in older wells is not as good as we would like it to be. So that tends to be where we have the failure. So this is showing these are called Sand Kings. These are big, portable, they run on like little conveyor belts, and they are full of proppant, and proppant is what's used when you do hydraulic fracturing. And proppant can either be natural sand. Once we embarked on active horizontal drilling and hydraulic fracturing, I'm going to let you pass these around. These are manufactured proppants that are ideally set for different porosity and permeability situations. So consider it like designer. And the idea of proppant is when you hydraulically fracture a reservoir, like you saw in the movie, and open up permeability, which we called unconventional or enhanced, if you don't stick little beads, micro beads, or things like sand inside those cracks, they close back up. And so the agenda of using proppant when you do hydraulic fracturing is to hold those fractures open. And so this is an example of the portable containers that are used. I think that you can see wheels on them. Then they bring them in one way and then they tip them on their end to be able to decant proppant out that can go into the completion process. In the video, you saw perforating guns, right? For they set the steel casing and then they perforate the casing and then they do the hydraulic fracturing. And that's ultimately, once they drill through those plugs, how hydrocarbons can flow out. This is a graphic that was actually in the Wall Street Journal some time back. It comes from the EIA, and it shows, again, the multiple casings to get through water tables for protection. We're going to talk about water use on the surface here in a moment. And again, a different visual of the horizontal leg, the hydraulic fracturing, and the proppant in there to help hold things open. The whole goal is to create man-made, human-made permeability in situations where we have porosity, but we do not have permeability, and so by definition, it's opening up an unconventional reservoir. I think I skipped it earlier in the slides just to make sure everybody knows hydraulic fracturing has been around since the 1940s. Horizontal drilling has not. And so what really was the tipping point, as I gently corrected one of the folks in class on Monday, is the real tipping point was the ability to drill horizontally and then apply hydraulic fracturing to that. Does anyone know why we call it fracking? That's great, you're fracturing the rock, but it's hydraulic fracturing is what the gas industry calls it. So who has been the biggest loser to natural gas taking off? Coal industry. So the coal industry really coined the word fracking because the idea for them is it sounded a little bit like some other F words, right? And so the coal industry had a big agenda. That doesn't mean you shouldn't say fracking, it's fine, I don't want to, but and the gas industry was really surprised, and for them it has always been more about the ability to drill horizontally. But it's interesting how words and nomenclature take on things, and I'm not here to argue that hydraulic fracturing and horizontal drilling are the end all. What I do know is it killed coal in the United States. I know it's being resuscitated a bit right now, and that natural gas has a lot of advantages. I'm going to give a whole lecture on Friday where we're going to spend a lot more time talking about my great concerns about natural gas too. But I just, there was a lot of evidence that just the coinage of fracking was something that the coal industry had a lot of interest in making natural gas look as negative as possible. Yeah.
Does fracturing occur due to the point charges or the water pressure?
I skipped a beat. It's because we're injecting high pressure water with the proppant in it. And there's, you'll see in a moment, like 0.5% or 1% at the most includes some things that are surfactants, things that help separate molecules off of things. And I've got a picture that touches on it here in a moment. This often ends up as a playful question on exams because this is what's called a Christmas tree. This is what you end up at the end after you've drilled a well, and it's just flowing naturally. You don't have to put a pump jack on it. On a geothermal well, it looks very similar to this. And in the beginning, when I taught this class, people had to manually go out and look at these things and turn knobs. And now these Christmas trees are all highly automated and sensors, and they can open valves and do things from a control room that's remote. So, but just knowing what a Christmas tree is, it's the assembly of valves at the top of a well once it's been fully drilled and completed. So I'm going to, this is kind of like a vocabulary Zoom thing. I'm going to take you through a lot of things. So fortunately, I already talked about what I care less about the trend here in the graph and just that you know what a duct is, which is a drilled, uncompleted well. 10 years ago, we didn't even have ducts. But the idea, people realized that because in the video, how you saw that you drill multiple wells from the same location. So one of the great breakthroughs of horizontal drilling was that it radically reduced the surface impact. Radically. We can get way more oil or gas out of a piece of land. And we used to have to, because the permeability was so low, we used to have hundreds of wells to get what we can get off of 3 or 4 pads, but have multiple wells radiating off of them. And so because it's so efficient to drill 10 wells at once, that doesn't mean you need to complete them all at once. And so that created this in-between state, which is being a duct. And so tracking the ducts is a form of natural, if we just use it for natural gas, it's viewed by the industry as almost like natural gas storage because it's wells you can actually bring online very quickly. Okay? So if the gas price really rose up high, oil and gas companies view this as a tranche of production they can bring on very quickly. This is showing the number of wells completed per location. So what that's saying is at a given location 10 years ago, if on a spot, there used to be 1.5 wells on average. Now at a given location, there's 3.25 wells per location. What that's saying is we're drilling more and more wells at the same place. Before, when you can drill horizontally, you can drill wells right next to each other. That's the same location. Before, we could drill horizontally. You couldn't drill a well right next to each other because they would compete with each other and they were vertical wells. Okay? So before, we had vertical wells here and here and here and here. And now we have horizontal well here that can, we have a location here and it can drill radially out and cover the whole piece of acreage. And so the big benefit that everybody lost when they got upset about horizontal drilling and hydraulic fracturing was the surface impact dropped dramatically and the number of wells you needed to drill. So the number of wells, there was a slide I showed you earlier about the total number of wells and what share was horizontal and vertical. So the story there is we have become the largest producer and we're doing it with far fewer wells. So producing. Why does the reservoir collapse? We already covered that. So because it's like concrete. So we're going to talk about tight oil and gas reservoirs some more. So they have little to no permeability. So that's why, and it's harnessing horizontal wells and that has taken us from importing 2/3 of everything to being the biggest producer. Now you could say, well, we really don't want to be in the hydrocarbon business. We want to have a renewable business, but it's only recently that solar's become economic and it is still not very efficient yet to use solar to power cars and deliver transportation. So we haven't figured out our whole system yet. So it has actually ended up being a useful non-military solution to energy sovereignty for the US so that we can bridge to the things we're investing in now. But we only get 1/4 to 1/3 of oil that's in the rock. Gas is more miscible. Gas moves through pore spaces much more easily. It's only CH4. Oil is a very complex hydrocarbon and a lot of it gets stuck in the rock, in the pore spaces. Who does dishes? Anybody do dishes? Have you noticed that soap and heat help you get the grease off? Okay? Soap and heat help you get oil out of the rock. Okay? So that's when we talk about enhanced oil recovery, we're injecting soap and we're injecting heat. Okay? Simple idea. I'm going to give you way more detail than you want that I'm going to click through quickly because I actually want to get to more Q&A. But we're going after rock, remember, that has pores. They're very small, but usually has very poor permeability. And these issues are what prevent us from getting more out of the rock. So we have these 3 stages when we find oil. This is just for oil right now, called primary recovery. And you do not need to know all the details of this. I really just want you to understand the concepts and not, get super wrapped on the details. So usually when you first puncture the reservoir, and this is under conventional situations, not unconventional, not horizontal drilling and hydraulic fracture, just normal conventional reservoirs. If you drill and you find something, you have natural flow or you have to pump it. Okay? And many of you have seen pump jacks. And you only get 10 to 12%. Secondary recovery is when you inject water into the reservoir to push more of the oil out of the pores. Or you can do some gas injection. And so a very famous place we do gas injection is Prudhoe Bay. Because Prudhoe Bay up in Alaska has a gas cap normally, associated gas in the reservoir, and there's no market for that gas. And so as they produce the oil, they take the gas and they re-inject it to raise the pressure of the reservoir and to get more of the oil out. Then we have tertiary recovery, which is only about 4%, 3 or 4% of global production, but in several parts of the world, we spend a lot of time and effort either using heat, thermal energy, we put steam in the ground, or we inject CO2, which Occidental does and some other companies in some Texas reservoirs, or we use chemical, which is like surfactants, which is like using dish soap, to inject it into the oil reservoir to break some of those molecules' bonds that's sticking to the rock and release more of the oil so that it can be produced. So this all adds up that world average overall recovery is only 30%. So that takes us back to our McKelvey diagram and said, wow, if technology came along like horizontal drilling and hydraulic fracturing, maybe we could get more, right? And that changes what our proved reserves could be once we prove that that enhancement of technology makes a difference. So we're not going to, this is details on primary, we're not going to get into it, but there's like 3 flavors of primary production. This is showing you more on primary production and how pump jacks work for people who are curious. So I apologize for, and sometimes we visit the San Ardo oil field, which is about 2.5 hours south of here. But right now we are not, they're in the middle of a merger, digesting a merger, so it's not a good time to visit. This is showing you secondary and this idea of re-injecting gas to get more or injecting water to get more out. And this is saying, and then we have enhanced, which is the third tertiary recovery, and that's where you're injecting steam or surfactants, which is chemical, or CO2. Gives you a sense of the mix. California is notorious for thermal EOR, especially down in Southern California. Texas is more where we're doing CO2 injection, and there hasn't been a lot of chemical going on. So this is really meant to be a flyby on the topic and not get too stuck on it. This looks like something where someone just put an algorithm in their Excel and said, well, it's going to go like that. But somebody important thinks that it's going to rise a bit going forward. This is a slide I made, which I'm really proud of, which we just update every year because I'm not really good at graphics. But it's this idea that if crude oil is $71 a barrel, 42 gallons in a barrel, it's actually really hard to find things cheap enough to shove in the ground to push that oil out and you still make money, right? So if you're going to put water in the ground to inject, it better be wastewater, it better be close by, you can't pay very much for it. So most of us don't think about these things at the grocery store in terms of barrels, the whole barrel of Ben & Jerry's, think of that. That'd be a really good party. So, but it's kind of like, so why do we only get a quarter of the gas or the oil, out of the ground? Because it's just too hard to spend the money to get more out. So this is showing steam injection, and they have dedicated steam injection wells that they inject steam one direction and they'll put steam injectors all around an oil well and push, and this tends to be used for oil that we call very heavy. It's very low gravity oil. It's not very high quality. We have a lot of that in Southern California. That's what a really ugly oil and gas field looks like. I visited it for the first time 45 years ago. It looks like an oil field, but you know what it is? It's a gigantic water treatment plant. because for every barrel that gets produced out of this field, or every 100 barrels that get produced out of this field, only 6 are oil. 94 of the barrels are ancient water that has half the periodic table in it and has to be treated very carefully. So interestingly, because of that problem, because we all need oil so badly, the largest reverse osmosis water treatment facility, and first to be built in California, was built on one half of this oil field, because otherwise Chevron was told they could not produce because they could not dispose of that water in the Salinas River because it's toxic. So seeing a gigantic water treatment plant that happens to be an oil field, and in order for, and these wells were first drilled in the 1940s, and they're very close together because it's a very impermeable reservoir. It's a very shallow one. There's a whole big story to this, but and it's right off, if you drive to LA on 101, you'll see San Ardo and you'll see this off in the distance. So I say the oil and gas industry will really have its act together when Martha Stewart can come in and say, this looks like a soccer field. What is that over there? Is that an oil well over there? There's a lot of gas production in northern Michigan, but you go up there and because it's like resort community, it's all surrounded by beautiful shrubs and landscaping. You don't even know it's there. Yeah.
In this slide where crude oil appears to be cheaper per barrel than other liquids, how are the high costs for production to get the oil being made up if the oil is being sold at a very low price?
It just doesn't make sense to inject any of those things. So if you produce, I mean, San Ardo has been producing oil $71 a barrel. In today's dollars, it's actually a pretty high oil price. The San Ardo is produced when the price of oil was $25 a barrel. So they're not willing to invest. It's a long-term asset, right? You have these long-term wells. These are wells, many of these wells are from the 40s. They have rigs they bring in called workover rigs that come in and clean up the old wells and kind of flush them out, kind of rotor-rooter them, let them keep producing. They're not high volume wells. And when I went there the first time, there were thousands of employees on the ground. Now they've automated all of it. So, they have 20 employees managing, a big. We have a more detailed, we can provide some information on San Ardo with the class to give you more of a sense of it. And I'm happy after class to talk more. I'm just constrained by time, but it is economic. But I think what's interesting, the state of California said no new wells, and we actually have laws in place to phase out internal combustion engines being sold in the state. So we're kind of in this, what do we do? And so San Ardo is owned by a company called Era that was a joint venture of Exxon and Shell. And they merged with the number one. They were the number 2 producer. The number 1 producer and the number 2 have merged because they're basically running a legacy maintenance business of managing the wells we have and trying both. That combined company is a huge customer for carbon management technology right now because they're trying really hard to comply with regulation in the state of California. My business partner in Woven Earth was head of strategy for the company that owned this field. And so she has a lot to say about, the efforts that were made. I think an issue that this shows is California is one of the most regulated states in the country, but they did not come in with a giant hammer and say, clean that thing up, get rid of that, because there's still this mentality of, oh my gosh, we might need that infrastructure if, we might need more oil, that kind of stripper well concept of let's not totally remove all this to we're clear we don't need it anymore. To me, it looks like a damn junkyard. But, when you go on a field trip there, you come away blown away by how well it's managed. The people are really impressive. There's people that have gotten degrees like yours, and they're out there making this thing run as well as it can. Yeah.
What happens with the treated water?
So 2 things. We have 35,000 EPA-approved injection wells in the United States, and some of them are on one side of this field. So there's 2 operators. One owns one side, one owns the other. It's not always how it works. One side has approved wells, the other one does not, and Chevron on the one that does not. Their only way to produce, because California said nope, was to build a very large reverse osmosis water treatment plant. So once that water is treated, it can be dropped into the Salinas River, and then they manage the stuff that comes out of that process. This is more on the injection of CO2, just trying to improve recovery. And this is a slide really meant to highlight the idea that, again, at San Ardo, when I first visited, there were 1,000 employees. Now there's 20 people on site at any given time. So radical automation of what's going on. This is an example of a workover rig, which is really just come in like going to get your teeth cleaned at the dentist, just clean things up, make everything work better. The ability to monitor wells remotely has been game-changing for, they're obsessed with safety for good reasons out there for the workers and for the community, and huge penalties in states like California, but not all states, for air quality violations, drilling mud violations, things like that. This is important to give you a sense. Remember, I talked about any well or a vintage of wells. Your biggest production is in the first few years, and then you go usually onto hyperbolic decline. So this is showing a vintage of wells drilled in a given year in the US and how the production from that vintage of wells declines. We have had net growth. This slide is out of date. We haven't been able to update it, but it's meant to show you that to maintain domestic production of gas, we have to keep drilling, because wells decline over time. That's just the reservoir pressure depletes, the volume of gas you can recover from the reservoir does not sustain the levels that you had at the beginning. But this flattening period, and as you see it up there, the average monthly production declines to a level that it stays at a low level for a very long time. And so, but that affects the economics of this for companies that are drilling and producing wells, is ideally you want to time things so that you're not bringing wells on in production when oil or gas prices are at a low level. So this is just to showcase the fact this is for an oil field, and this is very relevant to a field like Stanford that we've taken students to for decades, just because it's within 2.5 hours. Is basically there's a lot of facilities on the surface. At the wellhead, you get all these things. You need to separate them, and so there's different streams for separating them. And so the chemical engineers and civil engineers and water treatment experts and things like that that are part of the team are just as important as the people that are drilling wells and understanding the geology of the reservoir. And so without getting into all of the details of it, it's just to highlight the sophistication of the process. One of the things we'll talk about with natural gas as well is this is what has to happen with what comes out of the wellbore. This is before you get to refining the oil, right? And so this is to get you to a point at San Ardo. You have a lot of surface equipment for all of this. And then the natural gas plant liquids and the oil gets on a train and then on a tanker, and then it goes to refineries in Southern California, where it gets made largely into gasoline, jet fuel, and then other hydrocarbon products. And Diana's going to explain refining in great detail next week. So rig count and efficiency gains. So this is showing you drilling rigs right next to each other. So this is a neighbor's multi-well drill pad. It's 12 years old. But it gives you a sense of all this equipment moves in for a relatively short period of time, drills these wells, then the drilling rigs disappear, and then the completion equipment comes in. The completion equipment involves, as you saw in the video, a bunch of trucks. And those trucks come in and they have the fracking fluid, the hydraulic fracking fluid that is largely water, and then the proppant. And once that's all done, then they disappear. But one of the things in this, I talked about the social license and contract to operate in a community, is all the operators learn that they have to work with communities and time when those trucks come. You do not want the trucks coming through communities during rush hour. And very frequently, part of the social contract to operate is to agree when this is all done to repave roads in the community that needed to be repaired, and these trucks don't help those roads very much at all. So part of the currency of coming into communities, along with the landowners in the community getting royalties, is in order to have all this infrastructure activity going on, albeit for a shorter period of time than it used to, it is invasive. And so what do the drillers and operators of these wells give to the communities in exchange? This is showing you the global rig count breakdown. Where are the rigs today? They're mainly in the US. You see where the rest of them are. And this is very fine print, especially for an old lady like me. But the most important thing for you to notice is the largest number of rigs are in Texas and New Mexico, and that's because of the Permian Basin. So up there it's by state, up here it's by basin. You see the Permian has 313 out of probably whatever 450 rigs. So that is where the action is in the US, although these other basins, drilling and development is going on. This is just showing how does the rig count vary over time. It goes up and down, obviously. So oil, the rig count was very high. The rig count has dropped to these lower levels because of tight oil horizontal drilling. We don't need as many wells. So again, a well 10 years ago is very different than a well today in terms of its productivity. And some of the comments here are meant to reflect that. This slide would have helped your question earlier, saying this is what it looked like with vertical drilling, and look how much lower the impact is with horizontal drilling. So there's my cell phone metaphor. So way back when Tony and I were in school, I guess maybe I exaggerated how much they cost back then, but they're very expensive and very simple. And this is showing how wells have changed over time, kind of the cell phone equivalent, and this idea of zipper fracking, where they actually can come in and be hydraulically fracturing multiple laterals at the same time. So this is an interesting view. The Texans come up with words like this, like gun barrel view, but this is looking at a reservoir, a stack of reservoir in the Permian Basin in cross section, and showing these are basically the laterals. These are the lateral legs, not the vertical legs, but it's showing you in 1 square mile you can have this many wells. They're literally mining the hydrocarbons out of these layers of rock. But on the surface, you would never know it because there might be 4 pads for all those laterals. Does that make sense? So that's very different than drilling one so that's the well log there. So in the old days, we would just drill like 3 or 4 vertical wells on that, and you wouldn't get very much out of the ground. So it's pretty radical mining of hydrocarbons out of the ground that otherwise would not be released from the rock because there was no permeability. Does that make sense? Not advocating for it one way or another, just saying, trying to explain how it's working. This is showcasing where in the United States the active, I apologize for the fact this is a very US-centric conversation at the moment, but this is where the active areas are, and notably the Permian Basin is on the border of New Mexico and Texas. You see the Bone Spring here, this is the Permian, and the Delaware. So just because the aerial extent of the play doesn't necessarily mean that's where the most oil and gas is. It just might be spread out more. So I have one of these for gas. So this is showing what's happened. So gray is conventional gas. What we had 20 years ago was we didn't have any horizontal drilling or hydraulic fracturing to speak of. And so everything in rainbow colors is what we've gotten because we could drill horizontally. And so it's coded by the Appalachian plays are in blue. You just got to bow to Pennsylvania. First oil well, first gas well, first nuclear power plant. Texas gets all the credit, but Pennsylvania is really important. And so the dry gas plays are in orange, and then the green ones are plays where it's oil, but there's a lot of gas with the oil. And so that's actually good news, but it's also been tricky because we didn't have the pipeline capacity to catch all that gas. And so then what do? We flare it, which we're going to get to talking about in a moment. So this is another way to look at US crude production. And the gray is the rest of the US. And then this is just showing the Permian Basin impact since 2010 there. So showing the same information, just a different way. This is making the point that the amount of associated gas in our country is rising with the opening up of tight oil plays in the Bakken and in the Permian. So as we drill for tight oil, we're getting a lot of gas with that. We're not used to getting that gas, and there isn't the pipeline capacity to move it away, but we sure want that oil. So in a lot of cases, we vent or flare that gas, and that is not good for the environment. And it doesn't help the gas story. So this shows US tight, I was showing you gas before, this is the oil story. So this is showing the rise of US oil production, the Permian being such a key part of it. And what's in gray was what was conventional or not tight oil beforehand. So it's a big shift that's happened in the last less than 20 years. So, and this shows you production by state. Texas is way out there. New Mexico is right behind it. Those two, largely the Permian. Texas has more than the Permian. New Mexico, it's mainly the Permian. North Dakota's jumped up. And you see the mix of US production, how much is tight oil versus conventional. We pick on a state like North Dakota that with tight oil drilling, just a big leap in production has had a big impact on the economy of North Dakota, affected a big migration of people to go work there and support that production. And we have some interesting issues we weren't ready for that came as a result of this. So there's a lot of, this is nighttime satellite imagery of the flaring going on and the rigs and just a sense of what does it look like at night up in North Dakota where the circle is. And that wasn't there before. And then just the issue, there's insufficient pipeline infrastructure, and when we try and jam it in quickly and not take everybody into account and have a nice, thoughtful process, you get a lot of protests and a lot of concerns, which are legitimate. So it's great, we have this domestic energy supply, but there's a lot of complexity around it. The offshore part, which I'm probably not going to get to, is pretty readable, and let's see what I can do here. So today, we're really good. You see the flare. You know, this is North Dakota, oil and gas country development going on. But these are all the things we have to worry about. And I probably don't have all of them on the list, but it is highly regulated. Regulation's only as good as the people enforcing it, though, and industry often does push against regulations. So this is just kind of meant to landscape what some of the key issues are. We are perpetuating an industry in the United States where we really stand alone in terms of, we're the largest producer of oil and gas by a long margin. We have been decommissioning a lot of wells over the last decade that, were very, very low producers, but we're still, our average production in the United States is very low compared to other countries. Countries like Saudi Arabia have beautiful, expansive, conventional reservoirs. They do not need to drill horizontally or fracture anything. They have essentially miles and miles and miles of buried sand dunes that are pristine gas reservoirs with beautiful porosity and beautiful permeability. So their wells produce at very high volumes, and you kind of see the mix and the progression from there. So, kind of a joke I have is, what's a stripper well? It's not a well that takes its clothes off. It's this very marginally, but a very high percentage of our wells are stripper wells, and we have a specific subsidy to keep them operating to induce producers, owners of those wells, to deliver production. So a topic that's very hard for most people to understand is, what about the water? And I know there's some people in this room, including myself, who care a great deal about water. And so when you produce water from a typical oil well, most of it is ancient water, which is the reason we had to build the reverse osmosis water treatment plant on one side of the San Ardo oil field. The flowback water is what is coming back from the hydraulic fracturing. So it's a pretty small percentage of it. And in most cases, I think most people who know the business really well would say that water is actually really pretty good compared to the produced water, which has half the periodic table in it. So, what's in the flowback water is more like soap and sand grains from the proppant that went down. I don't want to hold to be an expert on that, but it's not very scary in the grand scheme of things. In general, how we've managed produced water has been these 38,000 Class II disposal wells in the US, where we've gotten in, as those wells, most of them existed before we went horizontal. So what's happened is, we said, well, let's inject more into the wells we have. In a few cases, which I'll show in a moment, that's triggered some seismic activity. But we are seeing issues, particularly on the border of New Mexico and Texas right now, with the Permian just growing so much. There's growing tension on where to dispose the water, what kinds of issues, how that's being managed and regulated. So without getting into all the text on this slide, it's really just meant to say, the plot is thickening. It is getting more complicated, even in parts of our country where people are kind of cowboys and saying, no, we're not going to worry about it. It is bubbling up literally as an issue. This is showing Oklahoma and what happened when, in a few, the geology associated with these injection wells really matters. And in a couple places are these long-standing injection wells, we put more water in them than they were used to, and it activated some faults. And we didn't know those faults were there. And it turns out that Mark Zobak, who's now an emeritus professor at Stanford, but is an expert in rock mechanics, seismicity, things like that. He's really the expert that came in to bear and helped figure, you see Walsh and Zobak there on the bottom, figured that all out. And so then they realized we need to moderate the volumes of water in some of these wells based on the geology of the subsurface. One of the things is to think about with hydraulic fracturing is, how much water do we use to inject into the ground, especially if we don't get very much of it back. We're stimulating this rock to create this pore space to get these hydrocarbons. The best math we have is that you can relate it to golf courses, livestock, mining. It is an industrial activity like all these other activities, but from a total quantity of water, it's not outrageous. What matters is the local story. And generally, hydraulic fracturing water is not potable water. It's water that they use wastewater, they use water that doesn't have a higher use. But there's pretty arid parts of our country like the Permian Basin, where just water in general is complicated and can be expensive. And so, just thinking about what are all the other uses of water is something that can create local tensions. And I don't want to sweep that under the rug to any extent at all. But for me, one of the things, when people describe a problem, I always want to try and find context for it and compare it and try and put it in a framework. And so that's what we're trying to do here. So this gets into water contamination issues. It does happen from time to time. It's very rare. And most of the time we have water contamination issues is with older wells where there's leakage and there's issues in the cement of the casing and leakage in that situation. So I don't want to say there's never any water contamination issues, but they are infrequent and usually with older wells, and that they need to be managed. So this gets to the idea of surfactants, of soap, and things like that. And this idea that what gets injected when we do hydraulic fracturing is typically 90% water, 10% sand or that artificial proppant we passed around, and then about 0.5% chemical additives that even people I know who work at the EPA say, yeah, they're kind of like things you have under your kitchen sink. That doesn't mean everything under your kitchen sink is great, but these are examples of the things that are used. In the beginning of horizontal drilling and hydraulic fracturing, the industry was a little secretive about their recipe, and that triggered a lot of fear. Devon didn't want Chesapeake to know what their frac fluid was. What happened very quickly when there was fear and concern about horizontal and hydraulic fracturing was everybody discloses in every state now what is in their hydraulic fluid so that everybody can see. No secrets. So these are disclosure, widespread. This is talking about the challenge, this is at a global level, talking about the challenge of when we produce gas, this could actually be in our, but it is affiliated with oil production too, this is just associated gas. So this is gas that's coming when we produce oil and what happens to it in different continents or regions. And the amount that is vented or fugitive that's going into the atmosphere is not good, because remember, methane is 80 times more potent than CO2. So that should be like a grand no-no. We should have big methane fees on that. And then flared gas is where we're burning gas rather than, but we still are releasing CO2 into the atmosphere, and we're flaring the gas because we don't have a market for it. So there's a growing movement there's a company called Crusoe that's now Series E. It's a clean tech company, and they have brought the capacity to grab that flare gas and use it for compute in the Bitcoin world. Rather than just have it be wasted. And so how can we bring load? How can we bring a use for the gas to where the gas is, rather than the only alternative is to try and build a pipeline to move it. And that is very hard to get built because communities don't want pipelines brought through their neighborhoods. So it's an interesting tension. This is just showing you what a natural gas flare activity looks like from a satellite, something to be concerned about, methane leaks. So this idea that the leakage of methane, if we're over 3% leakage, we lose all the benefit of gas versus coal. And in the Permian Basin, Stanford folks, Adam Brandt and others have identified that the amount of leakage, and Environmental Defense and others are all over this, but the leakage is as high as 9%. We're shifting to the offshore. And you were assigned a video about the Perdido, the largest oil platform in the world. And for those of you that haven't read it yet, or watched it, excuse me, I encourage you to do so. But at the highest level, one of the things to think about this particular spar production facility platform is, imagine this. It's 200 miles off the coast of Galveston, Texas. It's operating in water depths of 2 miles, so almost 10,000 feet. And the borehole, the well bore, is almost 2 miles deep as well. So, that's 4 miles of depth from the ocean surface, $3 billion cost. It's really quite staggering to think about operations of this scale. And with that, I want to pivot to just thinking a little bit about the characteristics of offshore drilling and production. So some key ideas is it's challenging and it's expensive. You have to have very elaborate guidance systems, and blowout preventers have to be installed on the ocean floor, often in situations that are in either somewhere from 100 feet to 5,000 feet, sometimes more, underwater. Sometimes like the Perdido, in situations where it's closer to 10,000 feet underwater. So the pressures you're dealing with and the forces, the physics of all that are really quite intense. In the US, offshore mineral rights are different than the onshore. There's no private mineral rights. We have state rights for the first 3 miles offshore, and then federal rights after that. And then we get into international waters, which generally there's a limited amount of oil and gas development in international waters. That tends to be politically challenging to figure out how to manage that. And a couple of key places where that topic comes up is in the Northwest Passage, and then in the areas of the receding Arctic ice right now, but also in the South China Sea, where there's ambiguity and friction around who owns what. The return on offshore drilling is large, but the capital risk is super high. So I tend to think of it as these are elephant resource opportunities, but they're extremely capital intensive to go after. And then a key idea when we think about offshore drilling and production, because this slide is really meant to frame key ideas, is that there's a lot around what we've learned in offshore drilling and production that we can apply to offshore wind, which is really a new and important industry. Particularly in Europe and in parts of Asia, those parts of the world have moved to offshore wind faster than the United States has, largely due to constraints on land and the NIMBY and banana issues. So the ability to use some of the same service companies and expertise about navigating in the ocean environment are something that are being really leveraged for offshore wind right now. So I think the diagram at the left is just meant to give you a sense to really think about the scale of these offshore operations. So I want to highlight the fact that the Bureau of Ocean Energy Management is the regulatory body for the United States for managing offshore oil and gas activity and lease sales and things like that, but also the organization stewarding offshore wind development and harvesting of battery minerals off the ocean floor, things like that. It's the regulatory body for energy development. Let's get a sense of the significance in the United States of offshore oil production. It's about 30% of all oil production globally, and it's less than that in the United States. In the United States, we're highlighting here the oil production versus the gas production in the United States, again, with the context that 30% of global production is happening in the offshore environment, really concentrated in about 5 countries. So how we drill in offshore, we use equipment like this, and the nature of the equipment we use, which you don't need to, get into in a lot of detail. The main point of this slide is we use different equipment in different water depths. And so you see the jackup rig in shallow water, the drilling barge in shallow water, the upper left and lower right. And then we have the drill ships or the semi-submersibles in deeper water. And then these are production platforms, not drilling. And so the Perdido is more like the spar that you see on the far right. And this is situations we alluded to in class where the facility that you see on the surface ends up becoming something that is staffed with hundreds of people who tend to have 2 half-day shifts. They're operating 24/7, 365. They come and go by helicopter or ship. In most of these, if not all of these facilities are anchored in some way, shape, or form, and with different roles of the anchoring and the floating aspects of the systems. So a big variety of platforms, largely for different water depths and different marine stresses. So this slide is meant to highlight what have been the biggest drilling related accidents in the oil and gas industry as opposed to production accidents. So on the drilling side, the biggest accident in terms of cost and damage is the Deepwater Horizon that happened relatively recently, 13 years ago. And the biggest accident in terms of human life is the Piper Alpha, which happened off the coast of Scotland. So very different geography, very different circumstances. And a list on the upper right of things that in this offshore environment, things that need, safety is very highly managed, but sometimes it's impossible to manage. And so there are issues seen here. What happened to the Deepwater Horizon is there were issues around the cementing the quality of the cement job on the well and blowout preventer failure. You can have unexpected drilling conditions. Sometimes you can have severe storms, and you can have a ship collide with your offshore facility. So there's an elaboration here. I went to UCSB as an undergraduate, and you see in the lower left highlighting the Union Oil platform that had a significant spill in 1969. So when I showed up at UCSB in 1980, that was still quite visceral in people's minds in the community, and a real hesitation to allow offshore drilling. In fact, after that spill, in California in 1969, there was no drilling allowed in state waters, that 3-mile zone, for a decade or two after that period of time. And then a new set of regulation and trust was established to reactivate drilling in state waters after that. So it happens. It happens very rarely, but when it does happen, it's very expensive. 47 to $50 billion of damage and settlements in the case of the Deepwater Horizon. Really great expense associated with it. So here's a bit about the Macondo BP Deepwater Horizon oil spill, the biggest in world history. Just giving you some information on that, and a link to a video that we're not going to show in class, but we encourage you to take a look at. This is a well that was basically out of control for 104 days. The blowout preventer had issues, a pipe broke. They tried something called a static kill. Lots and lots of oil was leaked. There were, fortunately, only 11 people were killed, but any loss of life is really tragic. And lots of species impact of birds, sea turtles, marine mammals, etc. So a big catastrophic event, which again doesn't happen very often, but when it does, it's something that requires, the settlement helped address some of this, but it requires a lot of regulatory and taxpayer response to clean up and address and deal with these situations. So it has reframed and reset further regulation for managing the offshore environment since this took place. This is another framing of U.S. oil spills. These are related not only to drilling, but to production. You see the Deepwater Horizon and its scale relative to other spills. And this shows where spills have been historically. I can at least report to you that the frequency of spills and the scale of spills has been declining overall if you pull the Deepwater Horizon out of the sample. And things have been relatively quiet on the spill side since the Deepwater Horizon. So another topic environmentally, when we think about the offshore environment, is thinking about how do we decommission these production facilities in the offshore environment. So there's more than 12,000 fixed oil and gas platforms in the seas worldwide, and they have a finite life. One of the things that's really interesting is they become essentially artificial reefs and very rich areas of biological activity. So it sometimes becomes complicated thinking about how best to decommission these. And in some cases, they plug and abandon the wells, and they basically cut the foundation of the platform and tip it into the ocean, because there is such a robust man-made reef of wildlife that has grown on the platform, that rather than removing it, they simply essentially permanently install it on the ocean floor. So, and obviously the bigger and deeper the platform, the more expensive it is to address in terms of decommissioning. But this whole idea of decommissioning onshore and offshore wells is becoming a robust area of stewardship, and oil and gas operators, needing to participate in this process and the regulatory enforcement to make sure we're doing this in the most thoughtful way. So to wrap up, we talked about the fact that the oil and gas have similar drilling processes. About a third of natural gas in the US comes from associated natural gas. The drilling processes and the equipment we've talked about is very common to geothermal, and you'll see it associated with drilling wells for carbon capture and storage as well. There's been a lot of innovation around hydraulic fracturing and horizontal drilling so that we can drill far fewer wells and have much higher recoveries, and we can drill faster, and we can have things like drilled but uncompleted wells, so we can drill many wells from the same pad and bring them online and complete them when they're needed in the market. Regulatory oversight, at least in the United States, which is what we understand best, has really risen, and I think has been established to provide communities and with a comfort around the social license to operate, staffing, which is true in banking and medicine and many other fields that we regulate, properly staffing, motivating, training, and rewarding the regulators to enforce these regulations is an ongoing challenge. And I think encouraging public dialogue, which fortunately social media and other things raise issues quickly to the attention of regulators in manners that was hard to do before social media. Offshore drilling and production is a relatively small part of the story, but a very important one. And going back to the regulation and social reasons, I think this whole pathway of community-based development, and it includes addressing audiences of rural communities, Native American communities, finding a way to get communities to participate in discussions and to educate the communities where oil and gas drilling and completion and other energy activities are taking place is essential. And with that, I'm going to take a bow.
If you want to learn more about this topic or other energy topics, visit our Stanford Understand Energy Learning Hub for free resources, including signing up for our monthly Energy Spotlight. Don't forget to subscribe to our YouTube channel and tap the notification bell to be notified for our newest content.